study is the constitutive, the linear elastic materials constitutive law. So, in order for me to talk about linear elastic materials, constitutive equations, we need to understand what each name implies. So we need to understand the classification of materials. So I'm just going to go through the different classifications of materials according to their constitutive equation. So by a constitutive equation, I mean I have a matrix of stresses. And I have a response, for example, utilizing the small strain matrix, which is half the gradient of U plus half the gradient of U transpose. And I'm looking for a relationship between those two. And I would like this relationship, if possible, to be one-to-one, because for every stress matrix I want a one. Just for the simplest case, I prefer that this relationship to be one-to-one, which means for every stress matrix I have one strain matrix, for every one strain matrix I have one stress matrix. And this relationship between the stress in the strain and the strain is what I call a constitutive equation. It tells me I can replace the stresses with the strains. I can replace the stresses with the strains in the differential equations of equilibrium. By replacing the stresses with the strains, I can write the differential equations of equilibrium in terms of the strains. But the strains are gradients of part of the displacements partial U1, partial U2, and partial U3 by partial x1, partial x2, and so on. And because the strains are functions of U1, U2, U3, I can actually solve the differential equation in terms of U1, U2, U3. And the most finite element analysis, or the finite element analysis procedures, solve the differential equation after replacing the stresses with the strains. And when you replace the stresses with the strains, you write the strains in terms of U1, U2, and U3, and your unknown would become the displacement rather than the stresses. The differential equation, as we said, was equal to divergence sigma plus rho b, let's say equal to 0. I'm going to replace the stresses with the strains. When I replace the stresses with the strains, this becomes function of U1, U2, and U3, and so the unknowns will become only 3 rather than 6. And that's why I need constitutive equation. So let's see the classification of materials. So usually, you find a new material, and you find a new material, you create a new material, and you assume a model, you take it to the lab, and you try to conduct some experiments to find if it's true that this material follows this model or not. So there are different models. And the first model is this material linear or not? If the relationship between the stress and the strain is linear, then the material is called linear, otherwise it's nonlinear. If relationship between measures, whatever measure of stress you put, measures of stress and strain is linear, I call this material linear. Otherwise, I call it nonlinear. Anything else is nonlinear. Now it's very important to realize that linearity and elasticity are not the same thing. You can have an elastic material that is non-linear. Elasticity talks about energy, elasticity refers to energy dissipation. So you can have a non-linear material. The relationship between the stress and the strain is non-linear, yet it's elastic. What do I mean by elastic? It means when I load and unload, I follow the same path, when I follow the same path, I'm not dissipating any energy. Because I'm following the same path, I'm not dissipating any energy, then this material is called elastic. If, on the other hand, as I load, I follow a certain path, and as I unload, I follow a different path that might go back to zero or not, then this material is inelastic. And the energy dissipated in the material is equal to this area between the two curves, and this energy is used, energy dissipated, in the form of maybe heat and damage or change in structure. So an elastic material is a material that does not dissipate energy. According to direction or material symmetries, so if this is the object or the material, if the relationship between the stress and the strain in this direction is exactly the same as the relationship between the stress and the strain in this direction, is exactly the same as this, the relationship between the stress and the strain in this direction, I call this material isotropic. It's independent of the orientation, the material is isotropic. Otherwise, it's anisotropic. There are different levels of anisotropy. General anisotropy, no symmetries. And I'll explain what a symmetry is. The second level is orthotropic materials. What are orthotropic materials? These are materials that have three directions of symmetry. What's a direction of symmetry? A direction of symmetry is a direction in which, when I pull, I don't see any shear strain. As I pull here, I don't see any shear strain. As I pull sigma on 1, epsilon on 2, epsilon on 3 is equal to 0. This is the direction of symmetry. Because the behavior is symmetric, I call this a direction of symmetry. An orthotropic material is a material that has three perpendicular called plane of symmetry, and we will study linear elastic orthotropic materials at the end, by the end of today. The other third level of an isotropy is transverse isotropic materials. Transverse isotropic materials are materials that have a preferred one direction of symmetry. So for example, the direction of E3, let's say specimen that has fibers in the direction of E3. So it has material. It has one plane of symmetry. Example. Symmetry along E3, or basically symmetry around plane perpendicular to E3. So it has one plane of symmetry, and the material is isotropic in the other two directions. So this is called transversely isotropic materials. Now, depending on the, usually material with fibers, usually this happens, materials that are orthotropic are usually materials, polymers or materials with fibers. So for example, if I have a typical orthotropic material, would be a material that would have fibers oriented in two different directions. In two different perpendicular directions. So for example, in this direction, fibers in this direction, and no fibers in the third direction. So you get different, when you measure the stress or the relation between the stress and the strain in the three directions, you get a different behavior. It's stiff in one direction, it will be less stiff in the second direction, and maybe weaker in the third direction. A transversely isotropic material is a material that has fibers only in one direction that may make it stiffer or weaker in that particular direction, but the behavior is the same in the other E1 and E2. We also classify materials according to homogeneity. Homogeneity, it means the relationship, if material is homogeneous, if the relationship between the stress and the strain I obtain for every specimen is the same. It's independent of the location of the specimen within a sample. If I have a sample, or I created a bulk of this material, the relationship between the stress and the strain at any point is the same. So the material is homogeneous. It's not getting stronger towards a certain, you can create, for example, what they call functionally graded materials, where young smallness here is small, but young smallness here is high. So this is a non-homogeneous material in terms of the stress strain behavior. But a homogeneous material whose response to loading is independent of the location is a homogeneous material. According to time dependence, a material, if the relationship or the response is time dependent, then the material is called viscous. Whose response to loading is time dependent. Let's just pause for a second here and see examples of things that are whose response is time dependent or viscous. Any material, in fact, has a certain time dependence. So for example, if you load it at a certain rate, you get a certain response. If you actually load it in a faster rate, you can get a stiffer response. So in fact, any material in the lab, depending on how you load it, if you load it really faster and faster and faster, you're going to get a stiffer and stiffer response, and this is called rate dependence. Every material is rate dependent at some rate, but for our engineering applications, we usually are really interested in at the very slow rates, and because at the very slow rates, there's not really change, and that's why the response that we usually use is the rate independent response, because usually when we put a material in a structure, it's usually in a very, the application of the load is very slow. Now, another two types of time dependence is creep and relaxation and stress relaxation. So what is creep? Creep is, I have a bar, and I put this bar under force F, and I measure the deformation at day 1, and then day 2. The bar is longer, and then day 3 the bar is even longer. Then this is creep, then this is creep, which is increase in deformation under constant if you visit any old concrete, not very old, but some of the old concrete buildings, you're going to find that the slabs are all sagged, and this sagging is just due to the creep of the concrete. So concrete creeps it keeps creeping for really long times, and some advanced concrete design methods consider the creep of concrete, take the creep of concrete into consideration. So this is a time-dependent response. Another one is stress relaxation. For example, you take a steel bar and you pull it. So you put it under a constant deformation, and then you start measuring the force. You put something in the middle here to measure the force. You put a load cell here. So you cut the bar and you put a load cell and measure the force. And then day 1, the force is equal to 100, for example, units. And then day 2, the force is decreasing, it's 90. This decrease in force under constant deformation is called stress relaxation. So examples, of course, when you put tension bars, the post-tensioning of steel bars, when you put when you have a concrete beam with post-tensioning cables, so you put the force, you put the cables, and you post-tension them, and then every now and then, because of stress relaxation, because the force inside that bar actually decreases with time, they have to go in and crank it up again and increase the force because of that stress relaxation. So in order to know how much force I have to, or how much I have to crank it, I need to study the stress relaxation of bars, or the stress relaxation of metals. Now, so this is how we classify materials. We're only going to look at the very basic type for this lecture, which is the linear elastic materials. After we go on our separate ways, geotechnical students will study the plasticity of soils. The structural engineers, the structural engineering students will study the non-linear elastic and the plasticity of metals. So let's understand the linear elastic material. A linear elastic material, basically, if I recognize a linear elastic material, this is a linear elastic material, I need to know how many constants, how many experiments I need to do to be able to conduct, to be able to fully explain the relationship between the stress and the strain. So given that the stress is equal to 6 material constants, given that the stress has 6, from the beginning, the stress has 9 components. And the strain, or a measure of strain, has 9 components. It's a linear elastic material. A linear material means the relationship between the stress and the strain is linear, which means for every component, I have 9 constants that I need to find. Because I'm saying the relationship between the stress and the strain is linear, so I'm saying sigma 1 is equal to, for example, 100, E11 plus 20, E12 plus, and so on. So I need to find those constants. So how many constants? I have 9 stresses and 9 strains, so I have 9, I need 9 by 9 constants, so I need 81 constants in general. Or actually before considering anything, just looking at the relationship, I need 81 constants because sigma 1, I will need 9 constants to find just sigma 1 because I need a constant multiplied by epsilon 1, a constant multiplied by epsilon 2, and a constant multiplied by epsilon 3, and epsilon 21, epsilon 22, epsilon 23, 31, 32, 33. But realizing that the stress and the strain are symmetric, because sigma 1, 2 is equal to sigma 2, 1, that means all the constants that are used for sigma 1, 2, I can use them for sigma 2, 1. All the constants that are used for sigma 1, 2, I can use them for sigma 2, 1, which means any constant that has 1, 2 in it is equal to the constant that has 2, 1 in it at the beginning, which meansCijkl is equal to Cijkl. And also because epsilon 1, 2 or epsilon ij is equal to epsilon ji, or let's just use kl, epsilon kl is equal to epsilon lk. Any constant that has 1, 2, I can also replace it with a constant that has 2, 1. And soCijkl is equal toCijlk. And because I want a simple relationship between the stress and the strain, I'm going to look at the stress as if it's a vector. Now we know that the stress is a matrix, but I'm just going to represent it as a vector because I need to find a relationship between the stress and the strain. So I'm going to replace the 9 components with a 6 by 1 vector with 6 components, and the strain with a 6 by 1 vector with 6 components, but I'm going to add epsilon 2 to epsilon 2, 1. So I have 2 epsilon 1, 2, which is the engineering shear strains. And the relationship is now fully described by 6 by 6, which are 36 constants. So right off the bat, because of the symmetries, I can say that the relationship between the stress and the strain is described by 36 constants. Now, so far, the only thing I considered was linearity. I actually have not considered that the material is elastic. When we say a material is elastic, we mean that there's no energy dissipation. There's no energy dissipation, mathematically speaking. That means that that there is a function that describes this integral. Because I'm always going up and down over the same path, that means that there's one function that describes this integration. Because there's one function that describes this integration, the stress is equal to the rate of change of this function with respect to epsilon ij. That's why it's called elastic. No energy dissipation. So let's see how this will help me. I will say that Cij, sigma ij, is equal to Cij 1, 1, epsilon 1, 1, plus Cij 1, 2, epsilon 1, 2, and so on, which is equal to the sum, but I'm going to not write the sum. Epsilon k. There is a summation sign, but k is repeated, L is repeated, so there is a sum sign. And I'm going to take partial sigma ij by partial epsilon kl. Partial sigma ij by partial epsilon kl will be just a constant Cij kl. I'm just going to do it with an example too, so that you understand what's going on in a second. Now partial sigma ij by partial epsilon kl is equal to Cij kl, and this is equal to partial 2u by partial epsilon kl epsilon ij. But I know that partial sigma kl by partial epsilon ij is equal to C kl ij, which is equal to also partial. Now because of the existence of this function, then these two have to be equal. And because these two are equal, you get that Cij kl is equal to C kl ij, which tells me this matrix is symmetric. C1122 is equal to C2211. So we have studied three symmetries in this whole class. The first symmetry is the stress matrix, and that was due to the equilibrium of moments. We've studied the strain symmetry, and the strain was symmetric because that's how we defined it, because we are looking for the deformation. We're looking for the extension, and the extension is usually described by a symmetric matrix. And now we also studied another third symmetry that's not related to the previous two symmetries. That new symmetry is the symmetry of the relationship between the stress and the strain, and this symmetry is only due to the energy considerations. Just to show that the stress and the strain, just to show that just for the stress to be derived from a potential, or only because this relationship has to be independent of the path, the existence of such a potential leads to that this stress matrix is symmetric. So this is symmetric because of elasticity. So now we have 21 constants. Now a general anisotropic material, a material that does not have any symmetries, when you pull in any direction, you actually get shear strains in all the directions. These are general anisotropic materials, and you need to devise a set of experiments to come up with 21 constants here. Now, if the material is orthotropic, before we, this Cij which is a function basically C takes the stress, the strain matrix and gives me a stress matrix. So this is, if you remember the end of chapter 1, this is a fourth order tensor. For every matrix, it gives me another matrix. How? If I change the coordinates of the coordinates of the system, then the components of C change according to this equation. And we studied this at the end of the fourth chapter. And this tells me that for a general anisotropic material, these constants really depend on the orientation. If I have, for me to find to find those constants, I have to define the orientations. I have a general anisotropic material. I have to define this is E1, this is E2, this is E3. Then the constant in the direction 1 will be different from the constant in the direction 2. Will be constant. It will be different in all the directions. Now, if I change my orientation, all the constants will change. And the relationship between the constants will be according to how the coordinate system is changed. An orthotropic material is a material that has 3 perpendicular axes of symmetry. And so when if these are E1, E2, and E3, that means if I pull along sigma on 1, I will not develop any shear. And if I pull along sigma to 2, I will not develop any shear. If I pull along sigma 3, I will not develop any shear. If I pull along sigma 1, 2, I will only develop shear in 1, 2. And if I pull along sigma 1, 3, I will only develop shear in 1, 3. If I pull along sigma 2, 3, I will only develop shear in 2, 3. So you end up with 1, 2, 3, 4, 5, 6, 7, 8. This should be 3, 3. This should be C2, 2, 3, 3. I think in the new version, in the new version of the book, this has been clarified. So 9 constants. If you're using the older version, so I need 9 constants to define the relationship between the stress and the strain. Now, how we realize that we need 9 constants? It's by the following. To come with having only or requiring only 9 constants, following procedure is adopted. Procedure is as follows. This is E1, E2, and E3. Then the relationship between sigma and epsilon is described by this. If I now change the coordinate system, and because of symmetry, I'm going to put E1, I'm going to put it on the other side, E prime 1, and keep E2, and keep E3. I'm changing the coordinate system and using a reflection. I realized that, but I'm just using the reflection. So because the material is symmetric, and the new sigma prime, because it's symmetric, will have to give me the same C, epsilon prime. Knowing that this relationship and this relationship are true, this is Q sigma Q transpose. This is equal to C. This is Q epsilon Q transpose. Knowing all of these, I'll be able to to ensure you'll have equations like this. Negative sigma on 1, 1, 2 is equal to sigma 1, 1, 1, 2. which tells me right away, C 1, 1, 1, 2 is equal to 0. So you do this 3 times, once by replacing epsilon prime, once by reflecting E1, another time by reflecting E2, another time by reflecting E3, and you're going to come up with that all these numbers are equal to 0. And in your text, there is a mathematical code that does this for you. Now, the orthotropic materials are described. Those 9 constants can be described using the 9 constants. Can be described using the following, which are more physical constants. They have physical meaning. Epsilon 1 will be equal to sigma 1 over E11, Young's modulus in the direction 1, minus Poisson's ratio 2,1 sigma 2,2 over E22, minus Poisson's ratio 3,1 sigma 3,3 over E33. Epsilon 2,2 is equal to negative Poisson's ratio 1,2 sigma 1 over E11. Just want to make sure I'm not making any mistakes. Plus sigma 2,2 over E22 minus Poisson's ratio 3,2 sigma 3,3 over E33. Where this is the Young's modulus in the direction 1. This is the Young's modulus in the direction 2. This tells me the ratio of the strain in 1 when I pull in the direction 2. This tells me the ratio of the strain in the direction 1 with respect to the strain in the direction 3 when I pull in the direction 3. Epsilon 3,3 is equal to negative Poisson's ratio 1,3 sigma 1,1 over E11 plus, minus Poisson's ratio 2,3 sigma 2,2 over E22 plus sigma 3,3 over E33. And epsilon 1,2 is equal to sigma 1,2 over G12, the shear modulus 1,2. So 2 epsilon 1,3 is equal to sigma 1,3 over G13. And 2 epsilon 2,3 is equal to sigma 2,3 over G23. And there's no reason why the shear modulus for this material need to be connected to the Young's modulus or the different Poisson's ratio. If you're modeling an orthotropic material, and you're, for example, using a finite element model, a finite element analysis software, the software will ask you for 9 constants. And the 9 constants will be this, this, and this. E11, E22, E33, G23, G13, G12, and 3 Poisson's ratio. I don't remember which one, or depending on the software, but maybe they will ask for those 3. And the last 3 Poisson's ratios can be obtained from the symmetry, or calculated from the symmetry of the matrix, because the symmetry of the matrix means that Poisson's ratio to 1 over E22 has to be equal to Poisson's ratio 1,2 over E11. Now, of course, that you have to be very careful when you write in the software, because when you input the materials into the software, because I don't remember whether Abacus, for example, asks for this one or that one. It asks for one and it calculates the other. A transversely isotropic material is a material whose response is isotropic in a plane. So assuming that the plane E1 and E2 is isotropic, which means the relationship between the stress and the strain is the same whether I pull in this direction, or I pull in this direction, or I pull in this direction, which means if I change my coordinate system and utilize E'1, E'2, and keep E3 the same, if I just rotate E'1, E'2, I should get the same relationship between the stress and the strain, the same constants between the stress and the strain. Now, by doing this, you figure out that we actually need only 5 constants to describe this machine. A constant, 2 constants that represent Young's modulus and Poisson's ratio in the plane of isotropy, which is E1 and E2. Another constant that represents the Poisson's ratio between E3 and the plane of isotropy. Another constant that tells me something about Young's modulus in the plane of in the direction E3. So now we have 1, 2, 3, 4. Isotropy means shear modulus is related to Young's modulus and Poisson's ratio, and we'll cover this when we talk about isotropic materials. And finally, 5, which tells me something about the shear between E3 and E1 or E2. So this relationship can also, instead of those 5 arbitrary constants, we can use 5 physical constants, and the 5 physical constants are epsilon 1 is equal to sigma 1 over that Poisson's ratio, that isotropic Poisson's ratio for E1 and E2, minus the Poisson's ratio for that plane, sigma 2 over E, minus Poisson's ratio 3, 1, sigma 3 over E 3. Epsilon 2 is equal to negative Poisson's ratio sigma 1 over E plus sigma 2 over E minus Poisson's ratio 3, 1. Oh, sorry, it should be 3, 2, but 3, 1 is equal to 3, 2 because E1 and E2, it really doesn't matter because E1 and E2, this is a plane of isotropy, so this is mu 3, 1, sigma 3 over E 3. Because Poisson's ratio 3, 1 is equal to Poisson's ratio 3, 2, because 1 and 2, plane of isotropy. Epsilon 3 is equal to negative Poisson's ratio 1, 3, sigma 3, 1 over E, and this are related because of symmetry. 2, 3 is equal to 1, 3, sigma 2 over E plus sigma 3 over E 3. 2 epsilon 1, 2 is equal to sigma 2, 1 over G, and G, as we will show, because of isotropy, is equal to E divided by 2, 1 plus Poisson's ratio. 2 epsilon 3 is equal to sigma 3 divided by G 1, 3, and 2 epsilon 2, 3 is equal to sigma 2, 3 divided by G 2, 3. So now I replace those 5 arbitrary constants with 5 constants that have more of a physical meaning. Young's modulus, Poisson's ratio by isotropy, so 1, 2, mu 3, 1, 3, E 3 is 4, and the shear modulus G13 is 5. So if you're doing a transversely isotropic material in, for example, in a finite element analysis software, it will ask you for 5 material constants, and I don't remember whether they ask for mu31 or mu13. It asks for one of those, but it asks for which is the plane of isotropy, what is Poisson's ratio and Young's modulus in the plane of isotropy, and what is Young's modulus in the direction perpendicular to the plane of isotropy. Isotropic linear elastic materials are those materials that whose response you get the same relationship between the stress and the strain independent of the current system. So the stress is equal to C multiplied by the strain, and if you change the current system, any current system, you get the same C. You don't have to change so you get the same constants. You don't have to change Cij KL prime is equal to Qi Ij KL and OP CIM QIM QJN QKO QLP. When you do this, you also get CIJKL. Whatever Q's you put here, you get the same constant. So in any point system, you get the same matrix representation. This means that the relationship between the stress and the strain will be you only need two constants. And these two constants are the Young-Small sample size ratio, and the relationship is given as follows: epsilon 1 is equal to sigma 1 over E minus Poisson's ratio sigma 2, 2. I'm just going to write the whole matrix: epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, 2, epsilon 1, 2, 2, epsilon 1, 3, 2, epsilon 2, 3, equal to a huge matrix, 1 over E, negative Poisson's ratio over E, negative Poisson's ratio over E, 0, 0, 0. This is a 6 by 6 matrix that only has two constants because G is equal to E divided by 2, 1 plus Poisson's ratio. And these two have the physical meaning. E is Young's modulus, Poisson's ratio is the ratio of the strain in any direction to the strain in the direction that's being pulled. So just one example here to show why we came up with a G. It's equal to E divided by 2, 1 plus Poisson's ratio. So assuming that the relationship between the stresses and the strains are described by a matrix, these are the stresses or the strains, and these are the stresses, and here we have 1 over G. So let's assume that we don't really know any relationship between G and E. How can we relate this G to E? To relate G to E, I just have to change the coordinate system, and after I change the coordinate system, I utilize the same relationship to show how G is equal to E. So I'm going to start from a state of pure shear. State of pure shear, the stress matrix looks like this: 0, sigma 1, 2, sigma 1, 2. And the strain matrix looks like this. Where epsilon 1, 2, 2 epsilon 2 is equal to sigma 1, 2 over that constant G. I'm now going to change the coordinate system and utilize a coordinate system that's oriented at 45 degrees. So E prime 1, E prime 2, and keep E3. So Q will be equal to cosine 45, sine 45, 0, negative sine, cosine, 0, 0, 0, 1, and write the stresses in the new coordinate system. Sigma prime in the new coordinate system will be equal to Q sigma, Q transpose, will be equal to sigma on 2, 0, 0, negative sigma on 2, 0, which is basically the new component sigma prime on 1, the new component sigma prime to 2, 0. And the strain in the new coordinate system will be equal to Q epsilon Q transpose, also will be equal to epsilon on 2, negative epsilon on 2, 0. Which is the new component epsilon prime on 1, epsilon prime to 2. Now forgetting about the original coordinate system, I know that the relationship between the stress and the strain is independent of the coordinate system, which means I can still utilize the same C. I can still utilize the same C to describe the relationship between the stress and the strain. So I can still utilize the same C, means I can write that epsilon prime on 1 is equal to sigma prime on 1 over E plus or minus Poisson's ratio sigma prime to 2 over E. So I'm using the same numbers, E and Poisson's ratio, that because they're independent of the coordinate system. Because they're independent of the coordinate system, I can use them here. And now I can replace epsilon prime with epsilon on 2, which is equal to sigma on 2 over 2G. I can replace sigma prime on 1 with sigma on 2 over E. And I can replace sigma prime to 2 with minus or plus Poisson's ratio sigma on 2 over E. And from here, you get that this shear modulus for this material to be independent of the coordinate system, the relationship between the stress and the strain independent of the coordinate system, you end up with E equal to, G is equal to E divided by 1 plus, E divided by 2, 1 plus Poisson's ratio. Throughout the development of the constitutive relationships between the stress and the strain, there are different constants that were developed along the way. Although the relationship is fully described by two constants. These constants could be the general. I'm just going to go up here. These two constants could be simply E and Poisson's ratio. Or you can represent the relationship between the stress and the strain using G and Poisson's ratio. Or using K and Poisson's ratio. Or using K and E. Or using G and E. Or using lambda and mu, which are called the Lemaire's constants. So there are different material constants, and the relationship can be fully described by any combination, by any of those two. We know G is equal to E divided by 2, 1 plus Poisson's ratio. K, which is the bulk modulus, is equal to E divided by 3, 1 minus 2 Poisson's ratio. And what is the bulk modulus? Is equal to epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3 is equal to the hydrostatic stress P divided by epsilon 1 plus epsilon 2, 2 plus epsilon 3, 3. The relationship between the volumetric strain, the volumetric stress, the hydrostatic stress and the volumetric strain. Another two constants are called Lemaire's constants. And as you will see in the assignment, the function of Lemaire's constants is just to describe, easy to describe the relationship between the stress and the strain. When you write it, the stress as a function of the strain, rather than the strain as a function of the stress. And lambda is equal to E Poisson's ratio divided by 1 plus Poisson's ratio, 1 minus 2 Poisson's ratio, and mu, which is G, is equal to E divided by 2, 1 plus Poisson's ratio. Okay, so I want to cover the restrictions and this simple. Okay, so we'll give you just 5 minutes. I'll start exactly at 10 past 10.